after this coming summertime, you take a dive into a swimming pool. Okay. Get on a plane. Go up north. Take a dive into an iceberg. See if you like that. See which gives, your noggin or the iceberg. Oh, that's a hell of a lot stronger than that solid state stuff. But as I said, if you are of a mind to in fact do this experiment, please let me know before you do it. I wish to consult my attorneys. And I want my students going to court on the basis that their screwball chemistry teacher told them to do an experiment which resulted in a concussion. All right? That means if I take this system and heat it up, am I going to favor the transformation as written? If I heat it up, this system? As we told you, you can't get pure NO2 or N4O4. At least not at normal laboratory conditions, so the equilibrium mix will always be what you got. Will this reaction be provoked to go left or right as written if you heat? If you want an external reaction to go, you want to supply heat? Hell no. Heat provokes bond breaking. So if I take my NO2 and N2O4 equilibrium mix, which we showed you before, I'm going to show you again, and raise the temperature of the mix, will I see an increase or decrease in color intensity? Increase or decrease in color intensity? Increase. Because I'll get more NO2 molecules in there at the expense of getting these molecules to fall apart. But if I cool, do I drive this transformation? You're damn right. Because cooling fosters bond making. So, for your benefit, I have here an NO2, N2O4 equilibrium system in ice water. Ice cubes slushed around the water liquid. And here, this is just weight to keep the damn thing immersed. I heated some water to a high temperature, the microwave we have back there. I don't know how hot it is. See any difference in color intensity? You're damn right. Here's the hot stuff, much more rich in NO2. Cool stuff, much more rich in N2O4 compared to this. Now then, on with the analysis, which has upset many good work done. This relationship you were introduced to yesterday. It's a very important relationship. Because direct determination of delta G0 is not easy. We have ways by which to measure changes in enthalpy without too much difficulty, but measuring this change in entropy, that's not so easy. So I got a problem if I now want to get delta G0 for the reaction. But the problem is alleviated by this relationship, which is derivable from fundamental thermodynamic considerations. I'm not bothering you with the derivation. I don't even have the derivation included in the notes. But I expect that if you load studies in physical chemistry, you will be shown this derivation. It's not difficult. And it is done in some general chemistry classes. Well, what's the benefit of this relationship? Shows us that if we're given a reaction, we can measure the equilibrium constant, and we calculate delta G0. That gives us our delta G0 value. You think it's particularly difficult to measure equilibrium constants? Now, it is true, given some of the equilibrium constants we've looked at, you will in some cases be determining very small numerical values. And those can be problematic to get because they may well involve measuring very, very small concentrations or partial pressures. And tiny numbers are difficult to measure reliably, oftentimes. But for the most part, evaluating equilibrium constants is easy because the system is at equilibrium. Its composition on standing no longer changes. So you can take all the time in the world you want. You're not in any rush. Kinetics is totally out of the picture when you're at equilibrium. And for a liquid phase system, like calcium carbonate associated water, devise a method to measure the calcium ion molarity reliably, the carbonate ion molarity reliably, and that one's easy to do because pH gives you a dead direct hand on its molarity. You calculate K. And so if you want delta G0 for calcium carbonate associated water, now you can get it. And this is why you see whole slews of K values tabulated for all sorts of reactions. Well, I shouldn't say you see because you probably haven't seen this yet. Because in my notes I haven't included tables of extensive K value information. But on our information sheet, for example, there are quite a number of K values there for the acids which are listed. At least most of the acids which are listed. And semi-soluble salts. And a couple of K values regarding information from complex ions. That's on the information sheet. Well, for this system, here's the equilibrium constant expression. Chemically. I've noticed that a number of you have a habit of doing equilibrium analysis, which will require you to pay attention to the equilibrium constant, by starting with the K expression in terms of a bunch of X's, from which point many of you often go astray. Write the chemical version of this equilibrium constant first. This is chemistry. And if you go past the chemistry, you are inviting disaster. Don't do that. Well, with the delta G sub F super zero information that's available in table 1 for NO2 gas phase and N2O4 gas phase, each at 25 centigrade, we get this number and this unit. Unit for this is pressure in atmospheres. Unit for this is pressure in atmospheres quantity squared. So ATM over ATM squared. So we get 6.69 per atmosphere. That's the equilibrium constant value for this reaction. And as we've noted, what happens to the magnitude of this number if I heat this system? Goes down, gets smaller. But if I cool the system, this number gets bigger. Now, for the equilibrium in question, I believe that I'm limited to cooling to about 21 centigrade. As my memory is right, at 21 centigrade, we have the normal boiling point temperature for N2O4. So we go below 21 centigrade, the N2O4 is going to start to condense, become liquid. We've got now a different equilibrium. In any case, with this, we apply one aspect of Dalton's law of partial pressure. Remember Dalton's law of partial pressure? We did this in 2045. Now let's put it to use. What are the two parts of Dalton's law of partial pressure? Dalton's law says doesn't say anything about one atmosphere. Dalton's law acting on or exerted by a gas phase solution is equal to the sum of the individual partial pressures for each component of the gas phase solution. So if you've got a mixture of three gases, the total pressure for the system is partial pressure of gas 1 added to partial pressure of gas 2 added to partial pressure of gas 3. 4 gases plus gas 4, etc. So this is just a two-phase gas component. I mean, not a two-phase, but two-component gas phase system. So, since we're operating at total pressure 1.00 atmosphere, I could write this in as an equivalent for partial pressure of N2O4 gas. I could have done just the same and written the partial pressure of N2O gas in terms of partial pressure of N2O4 gas and total pressure. And I put this in K and I solve it and I get these values. But what we want to do is get the composition of the system. In order to get the composition of the system, I need moles. So to get moles, and I use this. Yes or no? How many say, sure, I can use it? Because I want to see how many are wrong. What a rotten record. Hey, we're imagining that we have a piston cylinder beginning with 2 moles of NO2 gas. Does that correspond to the reaction equation we are analyzing? If I could do this, if I could start with 2 moles of NO2 gas at 25 centigrade, total pressure 1 atmosphere, what kind of volume am I talking about? Roughly. Given that NO2 gas has a behavior which is effectively describable by P equals nRT. What kind of volume would I have for this piston cylinder gas if I, in fact, did this experiment? Come on, you did this stuff in 2045. Let's put it to use. What kind of volume would I have? This is a pretty big piston cylinder gas. Small. 1 mole of a gas whose behavior is describable by P equals nRT. 1 mole of such a gas occupies what volume at 0 degrees centigrade? 22.4 liters. Remember that? That data point rings a bell. Well, and if I had 2 moles of an ideal gas at 0 degrees centigrade, I'd have 2 times 22.4 liters. That's about 45 liters. But I'm not operating at 0 degrees centigrade for this investigation. I'm operating at 25 centigrade. Will the gas occupy a larger volume or a smaller volume compared to its volume at 0 centigrade? Larger. You warm these gases up, they expand, don't they? So if I'm going to do this, I'm going to start with a piston cylinder that's got an internal volume of like 50 liters. It's kind of clumsy. Right? How would I get the exact volume if I wanted it? Based on 22.4 liters per mole. Would I do V1, T1, V2, T2, and that kind of stuff? We won't do that in my class. It's following recipes. I will take advantage of recognizing that when I warm gases, they expand. So I take my twice 22.4, which is 44.8 liters per 2 moles, which is the occupied volume of 0 centigrade, and multiply by 298 over 273 or 273 over 298. What will I do? are you going to do, Dalton? Multiply by 298 over 273, or 273 over 298. Where do I get these numbers? 298, 25 centigrade in Kelvin. 273 is 0 centigrade in Kelvin. Because I got to use Kelvin temperature to do this arithmetic. For a reason which I presume we're explaining in 2045, but I don't want to pursue that issue anymore. And I recognize the gas expands when I take it from 0 centigrade to 25 centigrade. So I got to multiply by the fraction that's going to make that initial volume larger. So 44.8 liters times 298 over 273 is going to give me a volume that's damn near 50 liters. If my memory's right, it's 48.9 liters if you multiply it up. Who cares? But will I, in fact, have that volume in analyzing the system? Will I have this volume? Will I observe this volume of about 50 liters? Huh? Hell no. We've already recognized that the equilibrium mix of NO2 and N4O4 at 25 centigrade is richer in N2O4, isn't it? That means I'm going to have a volume that's not near this 50 liters approximation. But I don't know what the volume is, do I? So if I look PV equals nRT, I don't know this and I don't know this. So you can forget this. I can't do that. Yet in the past, I've seen students take this relationship and at this stage of the game try to apply it and sit there and stew. One equation, do unknowns, you're stuck. But if I go back to the second aspect of Dalton's law, I can crack this puzzle. What is the second aspect of Dalton's law? We talked about some of the partial pressures equals total pressure. What's the other aspect of Dalton's law? Come on, most of you did this yesterday. The partial pressure of an individual gas in a mixture of gases is directly proportional to what? What? Mole fraction of that gas. Fancy schmancy X. Greek letter chi, capital version. That's mole fraction. The physicists intend abbreviational reference to mole fraction. This I can do. So all right. .68 atmospheres, because I am about to calculate moles of N2O4 based on mole fraction of N2O4. Equal. Times what? What do I put over here? What's the total pressure? One what? How tall are you? 72. What the hell does that mean? If you go up these units, this means nothing. You heard this sermon before? You're damn right. Would you like to hear it again? You're damn right. I'd like to make a rule here. All 2045 students, every one of them, have to take 2045 before that. Great wave of chaos set across the campus. Revolution would be upon us. How dare you make us work. How dare you require us to think? In turn, I would say, how dare you think you have the right to enter this institution of learning if you don't want to work and think? Out! That's the thing, isn't it? That I want you to work and think. But without these, you can't learn. Can't do it. On we go. Now then, from an algebra analysis standpoint, can I establish a relationship between moles of NO2 and moles of N2O4 in this system? Damn right. I imagine to do this experiment by beginning with 2 moles of NO2 and no moles of N2O4. So all right. Moles N2O4. At EQ, there you are. There's your favorite unknown representative. Maybe I should be like my algebra teacher and use A instead of X. Maybe I should use B instead of Y. Maybe I should use QZ to the 3/4 power divided by the square root of pi times 10 to the minus 38.63. Would you like to use that as your unknown representative? I can do it. And you can do it too. But I think you would be somewhat daft if you pursued that method of analysis. I mean, when I make this algebra definition, I call it anything I want. I can call it the mysterious format. You probably all be happy with that. If this represents moles of N2O4 equilibrium, then what is the algebraic representative for moles of NO2 equilibrium for this system? 2.0. Oh, let's just say 2, because I have no 2. I'm bad. I fall. Now you've got a 6.2. 2.0 minus, I'm listening, x or 2x, or 3x, or the square root of 2x, or 2x factorial. What is it? What did I write? Hey, don't forget the damn stoichiometry of this thing. If you want to make a mole of this, you've got to kill 2 moles of this. So if you want to make x moles of this, you've got to knock apart 2 x moles of this. And now I can put this stuff in and do the arithmetic. You can do that part. Take a look now at the graph on page 21A. If you read the graph on page 21A from left to right, because on the left side of the graph we are imagining to begin with 1 mole of N2O4 to do this experiment. You can start with it and the same result. And the graph shows you that as you proceed left to right with respect to the graph, N2O4 is decomposing. You start with about 1 mole of N2O4, you start with 1.0 moles of N2O4, about how much of it will decompose? About 20%, right? So this is telling you, if we did this experiment starting with 1.0 moles of N2O4, when equilibrium was achieved, we'd have 0.81 moles of N2O4 and 0.38 moles of NO2. About 20% of the NO2, N2O4 decompose? 19% to be round. No. Okay. So the graph is keeping with these circles. What would happen? If I did this investigation, starting with yeah, 1.0 moles each gas. What happened? 1.0 moles each gas. Will I still get N2O4 production and NO2 getting together to make N2O4? I start with a mole of each gas. Hey, let this thing touch. What's this tell you? This tells you that at 25 centigrade, the equilibrium mole ratio of N2O4 to NO2 is what? 0.81 divided by 0.38. Thus, at 25 centigrade, EQ mole ratio N2O4 NO2 is 0.81 over 0.38. What about 2.1 to 1, 2.2 to 1, something like that, or down there someplace. Okay. No, I don't care. If you're at 25 centigrade, I don't care what combination of these gases you put together. That baby is going to stop reacting because it will be at equilibrium when you get that mole ratio. So what would happen if I investigated this system by starting with a mole of NO2 and 2 moles of N2O4? That's not 2 to 1. It's a little bigger, 2 to 1. So if I start with 2 moles of N2O4 and 1 mole of NO2, what will happen? Some, but a little bit now only, of the NO2 will react to become N2O4. What if I start with 1 mole of NO2 and 3 moles of N2O4? Now some of the N2O4 will decompose. Yeah. Well, we want this thing to talk. Now then, in preparation for our next gathering, I want you to look at the acid-base table. Well, maybe you don't have to look at it. Maybe you will recall in the acid-base table. We have above hydronium, nitric acid, hydrogen chloride, sulfuric acid, and up here was perchloric acid. Those are the sum total of the 5 acids contained in our acid-base table. Okay. And we do not have K values for these 4. We have this. K is 55.5. Look at table 1. Show you another. I mean, there's all kinds of things you can do. I'm going to show you one more application you can make of this information that you see in table. Here's the task. Calc Ka for nitric acid. Can you do that with the table information in table 1? Let's look at the reaction equation. You recognize? If I can get delta G 0 for that reaction, then with this I can get equilibrium constant. What data do I need to get delta G 0 for this reaction? I need delta G sub F super 0 information for this, and this. But if you think further about this, do I really need to use table 1 to give me delta G sub F super 0 information for this and this? Yes or no? Why not? Why do I not need, in doing this analysis, have to pay attention to delta G sub F super 0 for water liquid and delta G sub F super 0 for hydronium ion AQ? Why not? How does delta G sub F super 0 for water liquid compare to delta G sub F super 0 for hydronium ion? We did this last time. How do they compare? They're equal! So when we apply Hess's law, those values cancel each other. So all you need is delta G sub F super 0 for hydronium ion AQ, delta G sub F super 0 for nitric acid liquid, apply Hess's law to get delta G 0 for the reaction, plug it in and get K. What kind of number, magnitude-wise, you think you're going to get for K? A nice big number? Well, you do it. We'll pick it up from this point next time, and if you do your arithmetic properly, you should get something exponent-wise that's almost 10 to the 5th. How about that? Nice big fat K? Showing you this is a strong X.